All right, if you're gearing up for that Unit 3 assessment, or maybe you just want to really get population ecology without wading through textbooks, this deep dive is definitely for you. We're aiming to give you a real shortcut today. We're going to unpack the big ideas using some really helpful sources we've gathered. Our plan: zero in on those core concepts, R versus K selection, basically, how species invest in their young found, then how that links up to survivorship curves, and critically, how we model human populations using things like age structure diagrams and the demographic transition model.
Exactly. And seeing how they all connect, that's the crucial part. It moves you past just knowing the terms, understanding why, say, bacteria populations explode, helps you grasp why human populations change globally. It's all kind of the same underlying engine.
Okay, let's jump in. Section 1, life strategies. R selected, K selected, and how long they tend to stick around. It really starts with energy, doesn't it? How species decide to spend their limited energy budget on offspring.
It's the ultimate biological trade-off, quantity or quality.
So let's start with R-selected species. The R stands for a high rate of population growth. These guys, they prioritize quantity. Lots of offspring, usually small ones, short lives. And the big one is little to no parental care.
Right, that's the key. Think algae, bacteria, frogs, most insects. Rats are a classic example. They reproduce incredibly fast. And it's a strategy that works well in unstable environments. If things change quickly, you want to get your genes out there fast.
Which makes sense why they're often invasive species too, like you mentioned with zebra mussels. They get somewhere new and just boom.
Right, short generation times. They don't hang around waiting.
Okay, so what's the opposite end of the spectrum? K-selected species?
These are the ones adapted to live near their environment's carrying capacity, or K. They flip the strategy completely. It's all about quality. Heavy investment in fewer offspring. Lots of parental care.
Like humans, elephants, whales. You expect the young to survive. It's actually a shock when they don't.
Exactly. But you brought up the oak tree earlier. That one seems a bit tricky. Produces thousands of acorns, but it's often called K-selected.
Yeah, that's a good point. The sources suggest it's about the investment per seed. An acorn is pretty big, packed with energy compared to, like, a dandelion seed.
Okay. So even though most acorns fail, the initial package gives each one a relatively better shot.
Sort of, yeah. It's a high initial investment per unit, which leans it towards K, even with the large numbers. It's a bit nuanced.
And that investment strategy, R or K, directly predicts how populations tend to die off. Which brings us to survivorship curves.
Right. 3 main types. Type I goes with K-selected species.
High survival when young, then a steep drop-off in old age. Like us, most individuals die old.
Then the complete opposite is type 3. That's your R-selected crowd.
Absolutely. Massive death rate early on. Think sea turtle hatchlings, fish eggs, those spiderlings you mentioned. Very few make it to adulthood.
And type 2 is the one kind of in the middle.
Yeah, a constant risk of death throughout life. Doesn't matter if you're young or old, the chance of getting eaten or dying is roughly the same.
Like squirrels, rabbits, ducks, things that have predators pretty much their whole lives.
Precisely. The strategy shapes the survival pattern.
Okay, let's shift gears to human populations now. Section 2, how we look at our own structure and transitions. We use age structure diagrams, sometimes called population pyramids. They're visual, right? Males on one side, females on the other, stacked by age group.
And that shape tells you a lot about a country's future. A wide base means tons of young people.
So the classic pyramid shape, like you see in, say, Nigeria.
Yeah, that indicates high birth rates, lower life expectancy, and predicts really rapid future population growth. Developing nations often have this shape.
Then you've got the more column or rectangular shape, more even distribution across ages.
Right. That's typical of developed countries like the US or France. Lower birth rates, longer lives, growth is slow, stable, or maybe even slightly declining.
And then there's the one that gets a lot of attention, the inverted pyramid.
That's where you have fewer young people at the base than middle-aged or older people. Think Japan, Italy, maybe Russia. It signals that the birth rate is below replacement level and the population is likely shrinking, or will be soon.
And that replacement level fertility, that's the magic number, isn't it? About 2.1 children per woman.
Yeah, the 0.1 is important. It accounts for kids who might not survive to have their own children. Fall below that consistently, and your population eventually shrinks.
Some of the sources controversially call this the rich country die-off, when developed nations hit that inverted pyramid.
It's a term used, yes.
Yeah.
But even if fertility drops below 2.1, the population doesn't just immediately start shrinking.
Ah, right. Population momentum.
Exactly. If you had really high birth rates in the past, you have a large group of young people moving into their reproductive years. Even if they only have 2 children each, the sheer number of them means the total population keeps growing for decades before it levels off or declines. It's like an echo.
Makes sense. And all this feeds into the bigger picture, the demographic transition model, or DTM.
The DTM is this really useful framework. It connects population changes to stages of societal development. You usually see it as a graph with 3 lines.
Okay, what are the lines?
You've got total population, usually in black, then the crude birth rate, let's just call it the birth rate, maybe green for new life, and the crude death rate, the death rate, often shown in red.
So, stage 1, pre-industrial times.
Right. High birth rates, but also really high death rates. Think pre-modern medicine, poor sanitation, lots of babies born, but lots died young. So the population's pretty stable, but low.
Then comes stage 2, the transitional stage. What happens first?
The death rate drops dramatically. This is key. Sanitation improves, basic medicine, better food supply. People stop dying so young.
But the birth rate
Stays high. Cultural norms around family size take much longer to change.
Sure.
Plus, less access to education for women, less birth control.
And that gap, high birth rate, falling death rate, that's where you get the population explosion.
That's exactly it. That's the period of rapid population growth we saw in Europe during the Industrial Revolution and what many developing countries are going through now or have recently passed.
Okay, moving into section 3. Let's connect this back to the broader ecological concepts. We talked about K for K-selected species. That's carrying capacity.
Right, the maximum number of individuals of a species that an environment can sustainably support long-term. For most non-human species, you can sort of identify a K.
And what keeps populations from just growing forever? These limiting factors. You have density-dependent factors.
Yeah, these are factors whose impact gets stronger as the population density increases. Think competition for food, water, space, spread of disease.
Like your wildebeest example, more wildebeest drink the water faster.
Exactly. And because animals don't usually, plan ahead or ration, this can lead to overshoot. The population blows past the carrying capacity.
And then what?
A die-off. The environment can't support them, so the population crashes back down, sometimes way below K. It's a common cycle.
Okay, so those depend on how crowded it is. What about density-independent factors?
These hit the population regardless of its size. A hurricane, a wildfire, a sudden freeze, a volcanic eruption. They kill a certain percentage, whether the population is big or small.
Got it. And thinking about carrying capacity on a global scale, there's this idea of biospheric degradation.
This concept suggests that as human population and development expand, building cities, farms, roads, we are actively reducing the carrying capacity, K, for almost every other species on the planet.
We're basically squeezing them out to make room for ourselves.
In a nutshell, yes. We modify the environment so much that it supports fewer non-human organisms.
Speaking of where organisms fit in, let's quickly touch on the ecological niche.
Right. It's more than just an address. It's the species' role or job in the ecosystem, plus the range of conditions, temperature, food, humidity it needs to survive and reproduce.
And there's a difference between the fundamental niche
Which is everywhere it could theoretically live if there was no competition or predators.
and the realized niche.
Which is where it actually lives, often smaller because of competition, predation, or other interactions. Like a nocturnal animal might be capable of being out during the day, but it stays out at night to avoid being eaten. That's its realized niche.
This leads to niche generalists versus niche specialists.
Yeah. Generalists are adaptable. They can eat lots of things, live in various habitats, like raccoons or coyotes.
To ecological jack of all trades.
Pretty much. Whereas specialists are highly adapted to one specific thing, a particular food source, a narrow temperature range.
Like the Anopheles mosquito needing specific conditions for malaria transmission, or maybe a koala just eating eucalyptus.
Exactly. Specialists can be very successful in stable conditions, but vulnerable if things change. Generalists might not be the best at any one thing, but they can roll with the punches better.
Okay, let's wrap this up. We've covered a lot, from R&K strategies driving survivorship, to how those same principles play out in human populations with age structures and the demographic transition. It really connects the micro-individual species strategies to the macro-global human trends. Understanding this framework, it really moves you beyond just definitions, hopefully giving you what you need for that assessment and beyond.
Absolutely. And here's maybe a final thought to chew on, connecting back to those trends. We talked about developed countries potentially facing population decline, that rich country die-off idea due to low birth rates in stage 4 or 5 of the DTM. But at the same time, we have biospheric degradation suggesting that overall human activity continues to shrink the carrying capacity for other species globally. So the provocative question is, even if populations in wealthier nations stabilize or decline, who ultimately bears the long-term ecological cost of global human development and consumption? What does that mean for biodiversity and the planet's overall decay? Something to think about.